All right, can you see the iPad screen?
Yes, sir.
Okay, so today I want to talk about LP spaces. So before I start, I want to mention that you have already seen an L1 space. Remember, I don't know if we explicitly said this or not. Suppose I have omega f mu, which is the measure space. Suppose I have a function f taking omega to r bar, which is measurable, right? I don't know if we actually said this, but we may have said that we say that f is in L1 if integral absolute value of f d mu is finite. Okay, so basically we have already, I don't know if we have introduced this notation or not, but this is a fact. You say that f is an L1 if integral absolute value of f d mu is finite. So now we're going to generalize it from L1 to LP. And basically the idea is going to be, I will say that f is an LP if absolute value of f to the p is integrable. That's what I'm going to do. All right. So let's write that down nicely. I am erasing this, I know, but I'm going to write it all out nicely. So we start with let omega f mu be a sigma finite measure space. So I will state this as an analysis result. Of course, by just changing the names, it follows to probability. Just one thing, we have used the symbol before. In case you've forgotten, R over bar is the extended real line, which is the closed interval minus infinity to infinity. All right, so I want to define what LP spaces are, right? So let omega f mu be a sigma finite measure space. So for f mapping omega to R bar, which is f b of R bar measurable, we will define, okay, now before I write this down, I want to say, I'm going to write this down. When you look at this, you really want to say that this is the norm of f. Now, the thing is, once we go ahead a little bit, you will realize that this is in fact a norm. But at this point, when I'm writing this down, it is not clear that this is a norm. However, we will use this symbol in anticipation that this thing is going to be a norm. Remember, a norm is just a length. Okay, norm is another name for length. Anyway, but at this point, we don't yet know that the quantity we're defining is actually going to be a norm. So here's what we do. We'll define this symbol. This looks like P norm of f, but again, we don't yet know that this is a norm. We define this as follows. This is defined to be the integral absolute value of f to the pth power d mu. And then we take the pth root of that. And this is if 1 less than or equal to p strictly less than infinity. Okay, so if p is greater than or equal to 1 but strictly less than infinity, to get this symbol on the left, which looks like the p norm of f, what do? I take absolute value of f, I take its pth power, I integrate it with respect to mu, and then whatever I get, I take the pth root of that. So that gives me this symbol on the left side, which I'm just marking with the red pointer. Again, at this point, you don't yet know that this is a norm. This is just a symbol right now. And we'll also define this symbol, which looks like infinity norm of f, but again, we don't yet know that this is a norm. We define this as follows. So you ask yourself, is there a k greater than 0 with the property that absolute value of f of omega is less than k almost everywhere? You ask yourself this question, is there a k greater than 0 with the property that absolute value of f of omega is less than k almost everywhere? Suppose there is such a k greater than 0. Now remember, this k is greater than 0, and so that means this family of k's has a lower bound. And so it will have an infimum. Well, you can take the infimum, and whatever the infimum is, that is what I'm going to take as the definition of this symbol. Now, if there is no k, I'm going to be taking the infimum of the empty set. Remember that by convention, the infimum of the empty set is infinity. Okay, so the greatest lower bound of the set containing nothing is infinity. And you know that the supremum of the empty set is minus infinity. All right. Okay, so that's what I'm going to do. I'm going to define the second symbol as follows. This symbol, which looks like infinity norm of f, again, we don't yet know that it's a norm. We define this as follows. We take the infimum of all k greater than 0 with the property that mu of the set of all omega in omega such that absolute value of f of omega greater than or equal to k is 0. All right, now again, this may get a little confusing, but remember all you're saying here is the following. If measure of the set of all omega and omega where mod f of omega is greater than or equal to k is 0, another way of saying that is that mod f of omega is less than k mu almost everywhere. All right, so here that's what I've done. I have omega f mu, which is a sigma finite measure space. Let f be a function taking omega to r bar, which is fb of r bar measurable. I'm defining these two symbols. Before I go any further, let me mention that these two symbols are meaningful. They may take value infinity, but they're meaningful. There's no problem with them being not meaningful. In other words, they're well defined. So note that the quantities this symbol for 1 less than or equal to p less than or equal to infinity, note that these quantities are well defined. They may be infinity, but they're well defined. Though they may be infinity.
So
Yes.
So f omega is bounded above by k, right?
Hang on. What did you? Can you repeat that, please?
Can we say that f omega is bounded above by k?
No, you cannot say that. That is the thing. That is the thing. Okay, so let me give you an example before I go any further. So this is okay. So let's say this is integral from 0 to 4. Let's say this is 4. Actually, this is a good point that will illustrate this. All right, so let this be 1. Are you with me so far? Ayush?
Yes, sir.
Okay, I'm looking at the interval from 0 to 4. Okay, so maybe my omega is the interval from 0 to 4. Take it open, take it closed, take it whatever you like. Okay. Then the graph of f is this thing. Okay, so basically f is just sitting constant at 1, and then abruptly here it jumps up to 4. And then again after it is sitting constant at 1. You with me so far? Okay, now let's call this point something, I don't know. This is not drawn to scale, but let's say it's the number 1. Would you say that this function is bounded above by 1? No, you would not. But let me ask you, what is, if I'm looking, what is the length of the set where it is bigger than 1?
It's a singleton.
Yeah, so what is the length of that set?
0.
0. So that means if you throw away a set of length 0,
okay, yeah,
it's bounded above by 1. Does that make sense?
Yeah, I understand, sir.
So we can say it is essentially bounded.
Right. That's another term for it. It's essentially bounded. Essentially bounded means that it's essentially bounded by 1. That means the set of points where it fails to be bounded by 1 has measure 0. In this case, we're talking on the line. So the notion of measure we're using is just length, which is just Lebesgue measure. So the point is here, if I said that this function is bounded above by 1 or 2 or 3, that would be a false statement.
Right.
However, if I looked at the measure of the set where the function is bigger than 1, that is 0. Right? So in this case, if you were taking, so actually this would be a good illustration of this. This number, this thing would be 1. Right? You will ask yourself, for which case is the function less than k almost surely? So the point is any k greater than 1 will work. For any k greater than 1, the probability of the set, no, not probability, the measure of the set where the function exceeds k is 0. And so the infimum of all these guys is just going to be 1. And so this infinity norm symbol is going to be 1. Does that make sense, Ayush?
Yes, sir.
Okay. All right. So can I erase this picture? By the way, there's one comment in the chat box. Oh yeah, sure. Yeah, Poonam, that's not a problem. Yeah. If you're at home, you can keep your camera off. It's just that if you're here, I'm going to pester you to keep your camera on. Yeah. All right. Can I erase this picture? It's not very nice.
So can we let that be? It would be a nice illustration.
It's not a very nice picture, but okay, I'll let it be. Okay. So let's leave that. Anyway, so I hope this clarifies what this infinity norm is. It is not the largest value the function takes. It is the smallest. That smallest is also false. It is the infimum of all values k, such that the measure of the set where the function is bigger than k is 0. All right. Anyway, the claim is that these quantities are well defined, though they may be infinity. And so now the question is going to be, what is L2? Well, before I write it down, let me just tell you what it is. So now I'm going to say L2 is the set of all functions such that this guy is finite. In other words, L2 is the set of all functions that the integral mod f squared is finite. Similarly, so somebody asked me, what is L4 over 3? Well, this will be the set of all functions such that mod f to the 4 over 3, when I integrate this, that is going to be finite. Somebody will ask me, what does it mean for f to be in L infinity? I will say, well, if this quantity is finite, then the function is in L infinity. So basically, now I'm going to, okay, so I need a little more room. Okay, so now I'll define what LP spaces are. Basically, L5 space is just the set of functions for which this guy is finite. That's it. L17 over 3 space is just the set of all functions such that this guy is finite, and so on. Okay, so let's just write that down. For any 1 less than or equal to p less than or equal to infinity, now we're making a new definition here. Let LP of omega f mu, let this be the set of all f mapping omega to r bar such that f is measurable and this symbol, which looks like a norm, but we don't yet know it's a norm, such that this symbol is finite. All right, any questions with that as to what LP is? So LP of omega f mu is just the collection of functions f mapping omega to the extended real line such that f is measurable. And further, this symbol, this norm fp is finite. All right. So now let me just add a couple of things. For 1 less than or equal to p less than infinity, f is in LP if and only if f is measurable and integral absolute value of f to the p d mu is finite. Okay, and f is in L infinity if and only if f is measurable and the measure, okay, well, basically, you know what this means. This means that and there exists k in 0 infinity such that mu of the set of all omega in omega such that absolute value of f of omega greater than or equal to k is 0. In other words, f is in L infinity if you can find a number k big enough such that the measure of the set where the function exceeds k is 0.
Excuse me, sir.
Yes.
Sir, is it necessary to mention that f is measurable? Because if we are saying that norm p norm of f
Yeah.
is less than infinity, that also
Right,
means
right.
norm is defined only for.
Okay, so the thing is, we are always going to be assuming measurability. So maybe you could say, I see your point. I see your point. You're saying that this symbol was only defined for measurable functions, correct? Is that what you're saying, Poonam?
Yes, sir. Yes, sir.
Correct. You're right. This symbol is only defined for measurable functions. So this symbol is not even allowed for non-measurable functions. So as soon as I write, if I say norm fp is less than infinity, then it's automatic that f must have been measurable. Otherwise, I cannot even apply this symbol to it. Yes, but this is maybe a little redundant. But yes, so measurability is always going to be assumed. Any questions? Yeah.
Like we had for expectations, like
Mhm.
if we have expectation of x cube defined, then we say that the expectations of okay, was it low? Yeah, expectations of x1 and x2 x2 are also defined. So can we say that for like LP spaces, if f let's say we are talking about L3 space and f and f3 is defined, so will f1 and f2 be also defined? So can we say that it's in L1 and L2 as well?
Very nice question. Not always. I think you have to be a little careful. If you're on a space of finite measure, yes, you can close your eyes and say yes. If you're on a space of potentially infinite measure, it can get a little subtle. I need to think about this a little more, but sometimes there can be competition, right? Suppose I look at 1 over x. If I square it, okay, keep the function 1 over x in mind, okay? Now, if I square it, then the behavior near x equals 0 gets worse because I have 1 over x squared.
Right.
Right. So if I'm trying to integrate near 0, I'll have trouble. But if I take 1 over x squared, integrating near infinity will be easier because it'll decay faster. Okay. That is just to give you some sense that funny things can happen, right? If you take 1 over x, if you square it, for integration, the behavior near 0 becomes worse, but near infinity, it becomes better. So if the point is, if you have a space of infinite measure, you cannot automatically say that. In the probability space, you can say that. In the space of finite measure, you can say that. Okay, but in general, maybe not. Okay.
Yes.
All right. Now, I just want to briefly remind you what a vector space is. You have seen vector spaces. So a vector space is a collection of objects called vectors. You can add 2 vectors to get a new vector. You can multiply a vector by a number, you get a new vector. And the operations of addition and scalar multiplication should satisfy some properties. Okay, you have seen the situation where you have vectors in R2 and R3 and Rn and so on. When you took your ODE class, you probably also saw that vector spaces could be spaces of functions. Anyway, so now here and actually we have already seen this sort of thing before. If you remember, we said that L1 is a vector space, right? We said this a couple of weeks back. I don't know when it was, but we made some comment that L1 is a vector space. Basically, we said that if I take 2 functions which are integrable, I add them, the result will be integrable. If I have a function which is integrable and multiply by a scalar, the result will still be integrable. Anyway, so the next claim is that these guys, so fix a P. Okay, so fix a P. LP of omega f mu is a vector space. That is the next claim. All right, by the way, shorthand, LP of omega f mu. In some cases, if f and mu are understood, we may just write LP of omega. Okay. We may also write LP of mu. Okay, so you will sometimes, or if everything is clear, you may also see LP. So of course, this is perhaps the most complete way of saying it. Sometimes if it's clear from the context, we may write LP of omega or LP of mu or just LP. Okay, that is just another thing to mention. All right, so now the next claim I have is that for any 1 less than equal to p less than equal to infinity, LP of omega f mu is a vector space. All right, so what I'm going to do is I'm going to prove this for the case that p is less than infinity, and I'm going to leave the infinity case to you. So proof. Okay, so consider the case p in 1 infinity. Okay, so here again now p is fixed. All right, I'm taking p in 1 infinity and it is fixed. Now I'm not messing with it. So let fg be an LP. By the way, I'm not going to say omega f mu again because you know what it is. Let alpha be an R. Okay, so what do we want to show? We want to show, or need to show, we need to show that f plus g is an LP, and we need to show that alpha f is an LP. If we can do these two things, then we'll have the LP of omega f mu as a vector space. Any questions? All right, so now let's check that f plus g is an LP. So to show f plus g in LP, we have to show that the integral absolute value of f plus g to the p is finite. Remember, I said that I'm looking at p in 1 infinity and I'm leaving the case p equals infinity as a do-it-yourself exercise. Okay? So p equals infinity, I'm leaving it to you to think about this. If you have some trouble with it, we can always discuss it, but I'm leaving it as a do-it-yourself. All right, so I want to show that integral absolute value of f plus g to the pth power is finite. All right, so here's what we'll do. So we'll say, let's look at absolute value of f plus g. All right, now by the triangle inequality, this is less than or equal to absolute value of f plus absolute value of g. All right, so far so good. Now let's take the pth power on both sides. So absolute value of f plus g to the pth power is going to be less than or equal to absolute value of f plus absolute value of g to the pth power. Okay, now pay close attention. Let's look at this right side here. This is mod f plus mod g to the p. Okay, let me make it a little simpler for you. Suppose a and b are both greater than or equal to 0. Okay. If I take a plus b to the p, okay, and of course here p is greater than or equal to 1. Now, okay, note I'm restricting my attention to non-negative numbers, okay? I'm not allowing negative numbers here. I'm taking a plus b to the p. What are the two possibilities? Either a is bigger or b is bigger. Suppose a is bigger, then this is going to be less than or equal to 2a to the p. Agreed? What is the other possibility? The other possibility is b is bigger, in which case this is less than 2b to the p. If a and b are the same, then you can use this guy or you can use this guy. At any rate, in either case, you can always use the sum of these two. So that's what I'm going to do next. A plus b to the pth power is less than or equal to 2a to the pth power plus 2b to the pth power. You guys with me? Of course, I can do this for a plus b plus c also. Again, they have to be non-negative, okay? A plus b plus c to the pth power, if they are all non-negative, this has to be less than or equal to 3 to the p, a to the p plus 3 to the p, b to the p plus 3 to the p, c to the p. You guys with me? That's all I'm using here. So that's what I'll do here. I'll say I have mod f plus mod g to the pth power. Either mod f is bigger or mod g is bigger. But anyway, as we saw in this argument, you got less than or equal to 2 to the p mod f to the p plus 2 to the p mod g to the p, right? And anyway, now let's see what we have here. Look at the thing I'm underlining. This is a non-negative measurable function. This is less than or equal to, look at the thing I'm underlining, that's another non-negative measurable function. So I know that if I have two non-negative measurable functions and one is smaller than the other, then the integrals will also respect that relation. Right? So integral mod f plus g to the p, which is what we are interested in, which is bounded above by this guy, is going to be less than or equal to integral 2 to the p mod f to the p plus 2 to the p mod g to the p. And of course, this here on the thing I just wrote, you can use linearity. So this is 2 to the p integral mod f to the p plus 2 to the p integral mod g to the p. You guys with me so far? Now remember that f and g are in LP. So what does that mean? That means that this guy has to be finite, and this guy has to be finite. Why? Because f and g are in LP. So this thing is less than infinity. All right, now measurability. Okay, so you have mod f plus g to the p is less than infinity. So f plus g is in LP. You guys with me? The scalar multiplication case is easier. Okay, this was the vector addition case because I took two functions f, g, and I added them. Right? Now I'm taking the case where I'm taking alpha f. So that is even easier actually. So if I take alpha f to the p, that is just going to be mod alpha to the p mod f to the p. So now if I take integral absolute value of alpha f to the p, this is going to be mod alpha to the p integral mod f to the p. Now remember f is in LP, so this guy is finite. And so this is finite. So yes, indeed, f plus g, if f and g are in LP, then f plus g is in LP. Also, if f is in LP and alpha is a scalar, then alpha f is in LP. So LP of omega f mu is indeed a vector space. Any questions with this? All right, so the p equals infinity case, I'm leaving it to you to fill in the details. If you have some trouble, we can talk about it. All right. Now, another thing I want to now remind you of is what is a norm, right? Basically, a norm is another word for length. You have seen this before. So this is actually just definitions from linear algebra or functional analysis, however you want to think of it. So suppose I have a vector space and it's a real vector space. Remember, in a vector space, you have objects called vectors which you can add, and you can multiply vectors by numbers. Now, in some cases, it is helpful to allow these numbers to be complex numbers. In some other cases, you allow the numbers to be real numbers. If you're insisting that the numbers you're using for multiplication are real numbers, then you have a real vector space. Okay. Now, what is a norm? A norm is just a notion of length. So let's complete this definition. So suppose I have a real vector space V. That means that the scalars I'm allowing are only real numbers. Then what is a norm? Note this symbol. A norm on a real vector space V is a function taking V to R such that, first of all, for any x in V, we have norm x greater than or equal. Let me write this in a different color. We have norm x greater than or equal to 0. All right, so for any vector, the norm must be greater than or equal to 0. Also, the other property is norm x is 0 if and only if x is the 0 vector. Okay. Now remember the 0 here, just to be clear, this is the 0 vector, not the number 0. The 0 vector in V. So that's the first property for a norm. The norm of any vector should be greater than or equal to 0. And the norm of a vector is 0 if and only if we're talking about the 0 vector. Second property is norm of alpha x is absolute value of alpha norm x. And this is for any scalar alpha. A scalar just means real number in this case, for any alpha in R, and any vector x, in other words, for any x in V. All right, the third requirement is the so-called triangle inequality. And that says that for any x, y in V, we have norm x plus y less than or equal to norm x plus norm y. Okay, so this last thing is of course called the triangle inequality. Any questions so far with what a norm is? Okay, remember norm is the same thing as length. Okay? And these are three basic criteria that any notion of length should satisfy. So now the question I want to ask is the following. Okay, so let P be in 1 infinity. Okay. Now suppose F is in LP. By the way, before I go any further, maybe I should just make a declaration here. All right, so I don't want to have to say this every time. So below, unless stated otherwise, we're always working on a fixed sigma finite measure space omega f mu. So I will not say again and again that we are on a fixed measure space omega f mu. Going forward, unless stated otherwise, we're always working on a fixed sigma finite measure space omega f mu. All right, so that's why when I say suppose f is an LP, you know that it's LP of omega f mu. All right, so suppose f is an LP. Okay. So I want to ask this question, does this symbol, right? Remember when we started a discussion of LP spaces, we defined this symbol, right? If I go back, right? When we started a discussion of LP spaces, we fixed a sigma finite measure space omega f mu. And then we defined this symbol that looked like a norm. And we defined this symbol, which also looked like a norm. Now my question is, does this symbol have any chance of actually being a norm? In other words, is it possible that this symbol will satisfy properties 1, 2, and 3 with V being LP? Okay. So in other words, I'm asking, i.e., will this satisfy 1, 2, and 3 above for V equals LP? Okay, now of course, some of these things will require work. In particular, the third one will require a fair bit of work. But I want to basically draw your attention to one of the things that will happen. I claim that unless we do some course correction and unless we do a little bit of clever footwork, the first one we may have a problem. So here's the answer. Some subtleties with 1. Okay, the longer answer is, as it stands, it will not satisfy 1. However, there is a little bit of fancy footwork you can do, and then you can ensure that 1 is satisfied. I don't want to write all that down, so I'm just going to say some subtleties with 1. Let's see what these subtleties are. So let f be the 0 function. Then, okay, let me backtrack. So let f be in LP, okay? Norm FP will be greater than or equal to 0, no problem. So that's not a problem. Norm f p is going to be greater than or equal to 0. So this first thing, which says that for any vector x, norm x should be greater than or equal to 0, this is true. No problem on this front. Also, if f is the 0 function, then this symbol is going to be 0. So when I look at this highlighted thing, one way is no problem. If x is 0, norm x will be 0, no problem. It is in the other direction that there is a subtlety. Okay, so if f is 0, then this symbol applied to it is 0. In other words, the 0 vector, yes, Ayush.
Oh, no, sir, sorry, I wasn't asking.
Okay. All right, also if f is 0, then now suppose this symbol is 0. Can one assume, no, not assume is the wrong word. Can one infer? Can one conclude that f is identically 0? Anyone want to take a guess?
Not necessarily, because it might be non-zero in a set of 0 measures.
Exactly. So it may, all you know is that it will be 0 almost everywhere. You do not know that it will be 0 everywhere. So the answer is no. Best one can say, well, actually what you can safely say, can safely say that f is 0 mu almost everywhere, but no more than that. We cannot say that f is actually the 0 function. Okay, so one way to do this is, to introduce something called equivalence classes. Basically, the idea is you have a bunch of objects and you define a relation and you say these two objects are the same if such and such relation is true. Now you do this in such a way that if you have a basket of items, then you can nicely partition these guys. All these guys are the same, all these guys are the same, all these guys are the same, all these guys are the same. So basically you're taking a set, if you like, you're blurring the distinction between some objects and you're saying, oh, these two, yeah, I'm going to think of them interchangeably. And you're doing it in such a way that now you're left with collections of objects. Those are called equivalence classes. But we can avoid getting into all that by just saying, you know what, here we're going to take this approach that when I say f in LP, okay, and I have G in LP, and F is G almost everywhere, then F and G are the same thing. Okay, so I will blur the distinction between two functions if they differ on a set of measures 0. So that is the remedy. If I make an agreement with myself, okay, if two functions are equal except on a set of measures 0, I will consider them the same function. If I do that, then the function which is 0 almost everywhere is the 0 function. Okay, so that is the little bit of subtlety that's there. The proper way to write it out is in terms of equivalence classes. I don't know if I want to get into that. And a simpler way to say this is, what we do is we will blur the distinction between two functions which differ on a set of measures 0. In other words, we will consider them the same function. If you do that, then a function which is 0 almost everywhere is no different from the function which is 0 everywhere. And so when you do that, then yes, then this thing goes through without any trouble. So that's what we're going to do, okay? So let me just mention that if you want to do it all very nicely, what you should probably do is you should look at equivalence classes. Just a second. I'm conducting a lecture. Okay, so if you want to do it really properly, you should probably think of equivalence classes, but we'll try and keep it simple here. So what we'll do is the following. So here's the remedy. The remedy is consider two functions. Again, these are measurable functions, okay? We are not allowing anything non-measurable into the arena at all. Consider two functions f, g as equivalent if f equals g, mu almost everywhere. If you do this with this in place, one above does hold. Okay, I don't want to write too much more. The reason one, this first property of the norm holds is because suppose norm f is 0, norm f sub p is 0, then f is 0 almost everywhere. But wait, now we have reached an agreement. We are going to consider two functions the same if they're equal almost everywhere. So if f is 0 mu almost everywhere, then f is f and 0 is g, and f and g are the same thing. Okay. Any questions with this? So this is how you get around this issue of point number one. Okay, you agree with yourself that I'm going to blur the distinction between two functions if they differ in a set of measures. All right, so going forward, so now the point is when you do any integration calculations, suppose f and g are the same almost everywhere. If you do any integration calculations with f and g, you'll always get the same thing. If you look at them at particular points, then they're trouble. But if you do any integration calculation, they're always the same thing. All right, any questions with that? All right, now the next thing I want to do is I want to start working my way towards getting these. By the way, do you agree that this second property is going to hold? Actually, we have already seen that here, right? Suppose I take mod alpha to the p, that's mod alpha to the p, mod f to the p. So the norm of alpha f is going to be, well, okay, so by the way, let me just add something here, okay? So just a couple of additional comments. So what did we do? Remember, I left the p equals infinity case for you, right? But let's look at what we concluded here. We concluded that integral mod alpha f to the p is mod alpha to the p integral mod f to the p, right? So if I take this equation that's highlighted, I can write it as follows. Norm alpha f p to the pth power is mod alpha to the p norm f p to the pth power. Do you agree that this and the highlighted statement are the same? Now I'm just taking pth roots on both sides. Okay, so taking pth roots, I'll have norm of alpha f. The p norm of alpha f is mod alpha. So basically, I'm just trying to say that in this lemma, you have already proved the second criterion for being a norm. Right? The second criterion for being a norm is if you multiply a vector by a scalar and then take the length, it should just be absolute value of the scalar times the length of the vector. So far, so good. All right, so now the goal is to kind of work our way up to the third property, and along the way, we also want to look at some important inequalities. Any questions so far? Okay, so now the next thing I'm going to do is I'm going to look at this lemma. This is called Young's inequality. As you know, I have been, occasionally raising stuff, deliberately writing it in class, because then that gives us a little more time to think about it. But I think in the interest of time, this thing I'm just going to leave as is, and I'll leave it to you to read this. So before I go any further, let me mention that this is a calculus result. This has nothing to do with measure theory on the face of it. It has nothing to do with probability. It has nothing to do with measure theory on the face of it. On the face of it, it is just a calculus result. It is a result about real numbers, okay? Okay, now let's also introduce this terminology, which I'm expecting you to remember because this will make our lives easier. Okay, so definition. Suppose P and Q are in the closed interval 1 infinity. Okay, so 1 is allowed, infinity is allowed. Say that P, Q are conjugate exponents if 1 over P plus 1 over Q is 1. Okay. Okay, so let's just keep this terminology in mind. It will reduce the amount of talking I have to do. Okay, if I say P and Q are conjugate exponents, you should know immediately. Okay, P and Q are taken from the closed interval 1 infinity, and 1 over P plus 1 over Q has to be 1. Okay, let's just think of a couple of examples. Suppose I take small p is 1, then Q has to be infinity. If I take small q is 1, then P has to be infinity. Agreed? And if I take small p is 2, then Q has to be 2. Okay, I'll leave it to you to play around as to, suppose I take the exponent 3, what is its conjugate exponent? I'll leave it to you to play around with that. But basically P and Q are conjugate exponents if P and Q belong to 1 infinity, and 1 over P plus 1 over Q equals 1. Okay. Now this will show up again and again. All right, so what is Young's inequality saying? It says, suppose I have, now in this case, note that in Young's inequality, I'm taking small p and small q in the open interval 1 infinity, okay? So I am disallowing them to take the value 1. I am also disallowing them to take the value infinity, okay? So suppose small p, small q are in the open interval 1 infinity, and they are conjugate exponents. In other words, 1 over p plus 1 over q is 1. Let x and y be any non-negative numbers, okay? Then x times y is less than or equal to x to the p over p plus y to the q over q. Okay, as I said, this is purely a calculus result. I will leave it to you to read it. Ordinarily, I might like to do it, but I think in the interest of time, it may be a little difficult to sneak all that in. So I will leave this for you to read. This is just a calculus result. It uses certain basic properties of what you learned in calculus. If I give you a differentiable function, how do you maximize it? Well, you take its first derivative, you set it equal to 0, blah, blah, blah. How do you minimize it? Same type of thing. All right, so can I just go ahead? I will leave this for you to read. All right, so Holder's inequality is saying, suppose I have P and Q in 1 infinity open interval, which are conjugate exponents, and x, y are non-negative numbers, then x, y is less than or equal to x to the p over p plus y to the q over q. Okay, so I'm just leaving this here, okay? This is what we'll use going ahead. So just the trailer for what's coming next. This is important enough that it's worth saying more than once. The next attraction is something called Holder's inequality. As said, we are always working on a fixed measure space omega f mu. That's a given. So let P, Q in 1 infinity be conjugate exponents. Okay, you know what that means? Note that here I am allowing P and Q to take the values 1 and infinity. So basically Holder's inequality says, so H, the Holder's inequality says that if F is an LP and G is an LQ, then the following things are true. First of all, F times G is an L1. And second, if I take the integral absolute value of Fg, this is less than or equal to this P symbol applied to F times this Q symbol applied to G. I'm trying to be a little too meticulous and not saying norm F sub P because we don't yet know that it's a norm. It's going to be a norm. Don't hold your breath. It is going to be a norm. But right now, since we haven't yet shown it, I'm just saying this. Good grief. Sorry about that. Decline. Okay, my apologies. Wait, there's the screen showing? Okay. Okay, so what the Holder's inequality is going to say two things. First of all, if F is an LP and G is an LQ, then F times G is an L1. That's the first statement. Second part of it says that if I take the integral of absolute value of FG, that is going to be less than or equal to the P symbol applied to F times the Q symbol applied to G. Again, these are going to end up being norms. By the way, let's note that what you have on the left side is actually just this one norm symbol applied to FG. Okay, so anyway, that's what Holder's inequality says. That's the next order of business. Questions? Again, the measure space is fixed. Again, all this will be nicely written out on the next page, so no worries on that front. Okay, so this is just repetition. This is a theorem. This is called Holder's inequality. Okay, so let P and Q belong to the closed interval 1 infinity. Note that 1 and infinity are being allowed. With 1 over P plus 1 over Q equals 1. Another way to say that is P and Q are conjugate exponents. Now suppose F is an LP and G is an LQ. Remember that until further notice our measure space is fixed. Then the claim is that F times G is an L1. And further, this norm 1, the one norm of FG less than or equal sorry about that. I log in here using the Ethernet. I think that's what it's called, the cable internet. And I think that every so often you have to sign in with your username and password, otherwise you get disconnected. So I think that's kind of what happened. I don't know what happens to the recording. Oh, the recording is continuing. How wonderful. All right, so let's pick up where we left off. Let me share the screen. All right, can you guys see the iPad screen? All right, so I'm going to first consider the case P is 1, Q is infinity. Now, what are we saying? We're saying that G is an L infinity. Remember, if a function is an L infinity, that means it is, as was mentioned, the term is essentially bounded. Translation, you can throw away a set of measure 0 and except for that set that you threw away, it is bounded. All right, so since G is in L infinity, you can find some number K greater than 0 such that mod G is less than or equal to K mu almost everywhere. And that is just by definition. Okay, so now what's going to happen? If I look at the absolute value of Fg, that is going to be less than or equal to K times absolute value of F almost everywhere. The reason for that is that, of course, absolute value of Fg is absolute value of F, absolute value of G. Absolute value of G is less than or equal to K almost everywhere. So this is less than or equal to K times absolute value of F almost everywhere. Okay, now I look at this thing that I'm underlining and this thing that I'm circling. And I'm going to say both these guys are non-negative measurable functions. And if one is less than or equal to the other, then the integrals will also respect that. So integral absolute value of Fg is going to be less than or equal to K times integral absolute value of F. But wait, integral absolute value of F is finite. Why is that true? That is true because F is an L1. Okay, so what I get is that integral absolute value of Fg is less than or equal to K integral absolute value of F, which is finite. In other words, Fg belongs to L1. So that proves the first part. Now we also have to show that this relation among the norms. Right? So you'll say, all right, what do you have? You have the one norm of Fg less than or equal to K times norm of F1. And this is true for any number K such that mod G is less than or equal to K almost everywhere. So now I'll take this equation and I will take the infimum over all such K. Okay. This highlighted equation holds for every K such that mod G less than or equal to K mu almost everywhere. So now take the infimum over all such Ks. What are you going to get? You're going to get on the left side is independent of K. So you have the one norm of Fg less than or equal to one norm of F. And then I'll get the infimum of all K such that mod G less than or equal to K mu almost everywhere. But wait a second, what is this? This is just the infinity norm of G. So you get norm Fg L1 is less than or equal to norm F1 times norm G infinity. Okay, it's the case when P equals infinity, Q equals 1 is of course similar. Just the roles of F and G are reversed. Any questions with this? All right, so now the slightly more tricky case we will actually work out here. So now we'll consider the case where P and Q are in the open interval 1 infinity. So now assume that P, Q are in the open interval 1 infinity. Of course, they're conjugate exponents. Okay, that goes without saying. All right, so now what can I say? So if, let me just copy what I want to show. Okay, so I want to show Fg, no. I want to show that F times G is in L1. I want to show that norm Fg in L1 less than or equal to P norm of F times the Q norm of G, right? This is what I want to show. I think you will agree with me. Now, do you agree that this will trivially be true if either norm Fp is 0 or norm GQ is 0 or both? Then the claim is trivial. Do you guys agree with that? All right, so let's think about this for a second. Suppose the P norm of F is 0. That means F has to be 0 almost everywhere. That means Fg is 0 almost everywhere. That means norm Fg is 0. And of course, that also means the right side is also 0. Okay, so if either the P norm of F is 0 or the Q norm of G is 0 or both are true, then the claim is trivial. All right, so now suppose that both these guys are non-zero. Note, I'm not talking of the value of F at specific points here, okay? I'm not saying, this is not the value of F at a specific point, this is the norm. This is what you get by taking absolute value of F to the pth power, you integrate it, take the pth root, okay? Then claim is trivial. So now suppose, so assume norm F, P, and norm G, Q are strictly greater than 0. Okay. Now here's what I'm going to do. I'll define capital F of X equals absolute value of F of X divided by the P norm of F, and G of X is absolute value of G of X divided by the Q norm of G. Okay. Remember again, here if the numerator is 0, there's no problem. We are assured that the denominator is non-zero. All right, so now what am I going to do? Now I'll use Young's inequality. Now, by Young's inequality, what I'm going to get is I'm going to get F of X, G of X is going to be less than or equal to, let's remind ourselves of Young's inequality. X, Y is less than or equal to X to the P over P plus Y to the Q over Q. So this is going to be less than or equal to F of X to the P over P plus G of X to the Q over Q. By the way, I'm not putting absolute values here because I already know that F is not negative. So I don't need to put absolute value. Okay. So now let's take this apart. What is this saying? So what is the left-hand side? Okay. What is the left-hand side that I'm just highlighting? Let's write on what capital F, capital G is. So what you get is, you get mod F of X times mod G of X divided by norm F, the P norm of F, Q norm of G. Right, this thing is going to be less than or equal to. So on the right side, what you're going to have, there's a 1 over P, right? And then you have this F of X to the P. So I'm going to get absolute value of F of X to the P divided by norm FP to the P plus 1 over Q, absolute value of G of X to the Q divided by norm G Q Q. Any questions so far? All right, now I will say that what do I have? I have function on the left side less than or equal to function on the right side. We have non-negative measurable functions. If one is less than or equal to the other, the integrals are going to respect that relationship. So now you integrate. So you'll get integral mod F of X mod G of, okay, so actually let me just simplify this a little bit. Remember, mod F of X times mod G of X is just mod of FG. So I'll have mod F of X G of X divided by, what are you going to get? You'll get norm F P norm G Q. This is going to be less than or equal to 1. You'll get 1 over P, 1 over norm F P to the P integral absolute value of F of X to the P plus 1 over Q, 1 over norm G Q to the Q integral absolute value of G of X to the Q. Any questions with this? And now you stare at this thing and you realize what this is. This is just the norm f to the pth power. In other words, it's precisely the denominator. And you stare at this integral mod g of x to the q and you realize it's just norm g to the qth power. So you look at this and you say, oh, this is just norm f, p norm of f to the pth power. And you look at this and you say, oh, this is just the q norm of g to the qth power. Right, so basically what's going to happen is that these two guys are going to cancel. These two guys are going to cancel. Take a different color. These two guys are the same. These two guys are the same. And so on the right side, you get 1. Right? You have 1 over p plus 1 over q equals 1. Okay, so now you have basically killed 2 birds with 1 stone. So now what you have is integral absolute value of fg less than or equal to p norm of f times q norm of g. By the way, if as soon as I write this, you know, so of course, integral absolute value of fg must be finite then, right? Because integral absolute value of fg is less than or equal to p norm of f times q norm of g. These guys are finite, so integral absolute value of fg must be finite. So thus fg is in L1. And now you stare at the left-hand side and you realize what this is. This is just the L1 norm of fg. And so you get Holder's inequality. This implies norm of fg 1 less than or equal to norm f p norm g q. Any questions? Questions? All right, so let me just, any questions with this? Can I stop sharing? Okay, so we got an email from the Dilip. You know, I think maybe sometimes there is a problem with not enough people filling in the course evaluation. So he's requested all the faculty to take 15 minutes in today's lecture to fill out the course reaction survey. So the next order of business here is Minkowski's inequality, but it's about 4:44. So I'm wondering if it might be a good idea to take a few minutes so that you can fill out the course evaluations. It's a shame already 2-3 people have gone. Okay, but let me stop the recording.